Hi, everybody. Happy Friday, and welcome to another calculus session. Today, we're going to be working through some of the material that this year is only part of the BC exam, but in previous years is generally considered mostly AB content. So for those of you that are just joining us for the first time today, quick reminder, for those of you that have been through a couple of these, your microphones are not on. I can't hear you. If you have questions, go ahead and just submit them as we're going through either the Q&A feature at the top of your screen or the chat feature at the top of your screen. And I'll try my best to answer them as they come through. If I don't get to your question, if I don't give it enough detail, we can talk about it at the end of this session. All right, so all of that being said, let's go ahead and jump right into what we are going to look at today. So again, this is BC material this year. This is kind of a mixture of AB and BC material in typical years. The first three things that we're going to look at today, integrating using integration by parts, and then partial fractions and improper integrals. This is all always BC topics. It's generally the end of unit 6 on an AP curriculum. This is always purely BC. The rest of this, average value, area between curves, and then volume, that's typically AB content that this year will only be on a BC exam. So for those of you that are not taking the BC exam, but are here and learning all of this today, that's awesome. This will be part of essentially what Calc 1 in college would be. So if you are going to start next year in Calc 2, this material will have been something that you would have learned during the school year. So I'm going to just run through some kind of more skill-based math for these first three. I'm going to show you one problem of each just to make sure that your notation looks good, your formulas look good, and all of that. And then we're going to talk about area, which average value of a function, I'm just going to kind of incorporate in with that area pretty quickly, and then work on navigating through the different volume formulas. So let's start with integration by parts. Integration by parts is kind of just some brute force math here. There's not a lot of theory that I'm going to work into these first couple of pieces. We're just going to do the math and see what happens. For any of this that is a definite integral type situation, of course, we can turn to a calculator and get an actual value for our answer. But if we are working on free response questions where the entire point is to show something, as in show how to integrate this using integration by parts, or show how to integrate this using partial fractions, show how to integrate specific things, we do need to make sure that that work looks good and we know how to do it. So integration by parts, I'm going to start with some background theory here and then go through the integration by parts. After I just said I'm not going to talk about theory, slight change, I'm going to briefly talk about theory. So integration by parts is the opposite of the product rule of differentiation. So think about if we have a product, so say we have f of x times g of x. Oh, sorry. We have f of x times g of x, and we want to differentiate that. So we want to differentiate that entire expression with respect to x. We would end up with the derivative of f times g of x plus the derivative of g of x times f of x in either order, because we are just adding together two terms. Order doesn't make a difference here. Now, if I then integrated both sides of this equation, so essentially almost undoing what I just did there on the left side, if I integrate both sides of this with respect to x, I will end up with, on this left side, just f of x and g of x again. I took the derivative, then I integrated, I'm right back where I started. But on the right side, I will have the integral of f prime of x times g of x with respect to x, plus the integral of g prime of x f of x dx. Again, just integrating both sides. Then I'm just going to do one quick manipulation of this. I'm going to take this term right here and solve for it and I'm going to write it on the left. So I'm going to take this term over to the left and this term over to the right, so that I end up with the integral of, and spin it around. I'm just going to warm up your brains a whole lot in one problem here. F of x times g prime of x with respect to x equals I guess I would have a negative sign there. Let's throw a lot of negatives in to start this as well. Equals negative f of x times g of x plus the integral of f prime of x times g of x with respect to x. Now that's because I just manipulated this in a very odd way to give myself this negative issue. Now I'm just going to multiply through by a -1 and flip all of those signs. So all that I just did there was really manipulate the product rule of differentiation. And this is the integration by parts formula. This is the integration by parts formula. It just looks a little bit different than the way that you most likely learned it in class. When we do this in an AP classroom, we typically use U's and V's. So I'm going to change my f of x into U and my g of x and g primes of x into V's. And then this formula ends up looking like this. If I have the integral of U dv, that is equal to U times V minus the integral of V, my g of x, du, my f prime of x. And this is the formula that you most likely worked with in class. This is the formula that makes integration by parts nice and easy and straightforward. But if it's helpful to conceptualize any different piece of this, it does come from the product rule of differentiation. Just like integration by substitution is essentially reworking the chain rule of differentiation, integration by parts is reworking the product rule. So in order to solve something here, so to evaluate an integral using integration by parts, we need to know what is U and what is V, or what is U and what is dV in the actual way that we would start this. So when we are solving a problem, so when we are evaluating an integral using integration by parts, we start with that U and that dV. That's what we're actually working with. That's what our integral gives us, U and dV. We would also then have du if we integrate that expression for U, and V if we integrate that expression for dV. So in this expression here, I'm going to make my t squared my U, and my e to the t dt my dV. And that should, again, that should make up your entire expression, your entire integrand. Then du right here would be dt, 2t dt, and v would just be e to the t power. So when I start working through this now, my integral becomes the integral of t squared e to the t dt, this is kind of hard to say, is equal to u times v, so t squared e to the t minus the integral of v du of e to the t times 2, I'm just going to spin that around actually and write that in the opposite order, 2t e to the t dt. Now here is one place where you can pause and just kind of think about how you actually want to set up your original u and dv. Your goal is to integrate this. That's what we have right here. So we need that to become as simple as possible. Our ultimate goal is to have something right there that I can integrate. So if we flipped this around, for instance, and I decided to start with u as e to the t and dv as t squared dt, in that case, when we integrated this, we would end up with something much more complicated. So it's a simple trial and error. If you flip it around, you get down to here and it's not easy, go back, do it the opposite way. So now in this case, I chose this problem because we get to do it again. In this case, we're not ready to actually integrate this. This is another integration by parts. So in this second integration by parts, I need another u and dv, and then du and v. And I'm going to go the same exact way here and say that u is 2t, and therefore du is 2 dt, and dv is e to the t dt, and v is e to the t. So now when we keep going here, I'm going to have t squared e to the t, that's this part right here, minus, and now I have all of this new integration by parts. So I'm going to put that in brackets just to make sure my minus sign carries through. So I have minus 2t e to the t minus uv minus the integral of 2 e to the t dt, my v du. And now that one is nice and easy to integrate. All right, so now when we go through this last line here, or almost last line, t squared e to the t minus 2t e to the t. And now I'm going to integrate this. When I integrate this, I get 2 e to the t. I'm going to subtract that negative. So I will end up with plus 2 e to the t. Now, here's the important part here, and this part you can kind of debate how you want to do this. But here's the important part. You're doing an indefinite integral right now, so at the end of this, we need to add on a plus c. Okay, we need to add on that plus c down there. Now, if you start to add different constants throughout your steps, those constant values are going to be different. Okay, those constant values are going to be different. So this value of c would be different than a value of c if we just did, for instance, a value of c right here. I tend to just not deal with it until the end, but make sure you do add on that plus c at the very end. All right, partial fractions. One more type of integration that we can work on. Again, just a skill, not a ton of theory here, but just a skill that we have to be able to do if we need to write this one out. And partial fractions has to do with, think about all the way back to 5th grade, 6th grade, 7th grade, whatever it is, when you are adding two fractions together. It has to do with adding two fractions together and therefore needing to find a common denominator. So if we're integrating by partial fractions, just looking at this integral to start, there's nothing fun that we can do. We kind of have no ability to integrate this unless we just throw this into a calculator. But if we are going to do this one by hand, if we're going to try to work through it by hand, we can use partial fractions if we can factor the denominator into different factors. So we can factor this denominator into x plus 2 and x plus 1. My numerator is just going to stay as 5x plus 8 dx. Now the theory here is that if I had this expression, let me change colors. If I have this expression, I could have created that by adding two fractions together. One that had a denominator of x plus 2 and one that had a denominator of x plus 1. I could have started with two different fractions and added them together. So I'm going to go off to the side and we're going to figure out what those two fractions were. That's the idea of partial fractions. So I have 5x plus 8 over x plus 2 times x plus 1. And we are going to say that we created that by adding a fraction that had a denominator of x plus 2 with a fraction that had a denominator of x plus 1. Their common denominator would have been x plus 2 times x plus 1, or x squared plus 3x plus 2. I don't know what those numerators would have been. Those numerators would have been something that ended up, when I did all of my multiplication to get common denominators, ended up being 5x plus 8. And that's exactly our goal right here, to figure that out. So 5x plus 8 over x plus 2 times x plus 1 is equal to, now I'm going to actually add these two fractions together on the right. So I'm going to have a times x plus 1 plus b times x plus 2 over x plus 2 times x plus 1. And all I'm going to do is clean up that right side numerator. So 5x plus 8 over x plus 2 times x plus 1 equals ax plus a, I'm unfactoring everything, plus bx plus 2b over x plus 2 times x plus 1. So now what we need to do is stop and line up what we started with what we now created for ourselves. So we started with this 5x, 5 as my coefficient of my linear term. So a plus b must somehow equal 5. Ax plus bx equals 5x. So I create this second equation for myself. A plus b has to equal 5. And then I also know that a plus 2b, my constants, has to equal positive 8. So a plus 2b equals positive 8. And now, I went off to the side again. Now I created for myself a linear system of equations. And I can solve this by substitution. I can solve this by elimination, whatever method is easiest. I'm just going to subtract, in this case, the second equation from the first and get negative b equals negative 3, which will tell me that b equals 3, and then therefore a equals 2. So b equals 3 and a equals 2. So now I've figured out, just zoom out and let you focus on all of that for a minute. Now I figured out what my a and my b are. So I can rewrite my integral. Now I'm going all the way back to here. I can rewrite my integral as 0 to 1, the integral from 0 to 1 of this. Of this a over x plus 2 plus b over x plus 1. And I now know what a and b actually are. I know that a is 2 and b is 3. And I'm integrating all of that with respect to x. So all that we did here was take this original 1 fraction and break it into 2 fractions that are easier to integrate. I have the ability to integrate these based on common integral knowledge that I know. So I'm going to do 2 different things at one time here. I'm going to split this so that I'm integrating term by term, but I'm also going to pull out the coefficient. And say that now we are here. And we have the ability to integrate something that looks like this really nicely, because if we think back to our function f of x equals the natural log of x, for instance, y equals the natural log of x, f of x equals the natural log of x, however you want to think about that, we know that the derivative of that function is 1 over x. So if we are evaluating this here, the integral of 1 over x plus 2 is the natural log of the absolute value of x plus 2. And I need to evaluate that. I'm going to use brackets for my evaluation here just because I have those absolute value bars. I need to evaluate that at 1 and 0. And then my integral from 0 to 1 of 1 over x plus 1 dx, my integral of 1 over x plus 1 is the natural log of the absolute value of x plus 1. and I need to evaluate that at 1 and 0. And now we got through the partial fractions part, but I'm going to keep this going just because it illustrates some really great logarithmic properties that I want to make sure you can remember. So I'm going to take this a couple steps further. So we would have here 2 times the natural log of 3 when I evaluate this at 1, minus the natural log of 2 when I evaluate this at 0, plus 3 times the natural log of 2 when I evaluate this at 1, minus the natural log of 1, which is 0. So we end up with a 0 at the very end. So this is 2 times the natural log of 3 minus 2 times the natural log of 2 plus 3 times the natural log of 2. Now, natural log properties, when we have this constant or this coefficient out in the front of our natural log term, we know that that works as an exponent. So this is the natural log of 3 squared, so the natural log of 9, minus the natural log of 2 squared, so the natural log of 4, plus the natural log of 2 cubed plus the natural log of 8. If I condense this, condensing 2 logarithmic terms that are being added together means that we are condensing into 1 logarithmic term with a product in our argument. If we're condensing natural logarithmic terms that are being subtracted, then we will use division within our argument. So I will end up with here the natural log of 9 times 8 over 4, or the natural log of 9 times 2, so the natural log of 18. This entire integral evaluates to the natural log of 18, which is exactly what we would get if we did throw this giant expression, the one that I already highlighted in purple, this giant expression into our calculator to get that final value. Again, even though I know that we can do that, I know that we can throw this into a calculator, get a value, make sure that you can work through this partial fraction work. This is a pretty common BC type integration free response question. That was a very long statement, but common integration type problem, free response problem on a BC exam does ask you to find the partial fraction representation of a specific integrand and then evaluate the integral. Great to check in a calculator to make sure you get there, but you do need to generally need to go through all of this first. Okay, improper integrals. Let's look at this one very quickly. I'm going to go through the first one in a little bit more depth than the second one. There are 2 types of improper integrals. The first type is when one of our bounds is infinity or negative infinity. And the second type is when there's an asymptote somewhere in between our bounds, or discontinuity somewhere between our bounds. So if we look at this first integral, we're being asked essentially to find the area under the curve of x times e to the x, but we have an infinite bound, which seems very misleading. It seems like there cannot possibly be a finite area with these infinite bounds. There can be. It is one of those fun tricks of calculus. And when we do this, we work with a limit. We can't actually integrate something with a limit, or sorry, with a bound of infinity, but we can use a limit. So when we do this, we say, we are going to change this to the limit as t approaches negative infinity of the integral from t to 0 of x e to the x dx. And I'm choosing t, oh, let me use a different color. I'm using t here. It doesn't matter what variable you use, as long as you are not going to use the same variable you have in your actual integrand. Pick something to replace that negative infinity with and turn that into a limit situation. So when we do this, what we really are going to do here is evaluate this integral. This one is going to use integration by parts again. evaluate this integral, and then take the limit of that final situation. I'm going to go through this one because there's some good notation to just be careful of as you do this. It's worth working through this notation wise, even if you conceptually know what's going on here, just to make sure you have parentheses where you need to have them, and you evaluate your integral pieces where you need to, and all of those different things. So as I work on my integral, this is an integration by parts problem. I need to know a u and a dv, and then therefore we'll need a du and a v. So I will start this one as u equals x and dv equals the rest of my integrand, e to the x dx. Du is then dx, and v is e to the x. So when we set this limit up, I'm going to be evaluating the limit as t approaches negative infinity of this whole integration by parts expression. So I'm going to bracket that off. And this whole integration by parts expression works as u, v, so x e to the x. And this time I have a definite integral, so I need to evaluate that at 0 and at t, or at 0 minus the evaluation at t, minus the integral from t to 0 of v du, of e to the x dx. And then you can kind of take this several different ways if you want to. If you want to already break up that limit, so you break this into the sum of the limit of this minus the limit evaluated at this, you can. If you want to just keep going with these giant brackets and clean it up at the very end, you can do that as well. And I'm going to take it that way for us. So we have the limit as t approaches negative infinity. If I evaluate this, I'm going to go ahead and evaluate this part right here. If I evaluate x e to the x at 0, that is 0. When I evaluate x e to the x at t, that would give me t e to the t, and I would be subtracting that. I have the evaluation at 0 minus the evaluation at t. And then minus my integral from t to 0 of e to the x dx. The integral of e to the x is e to the x. And I'm going to evaluate that at 0 and at t. And I'm still taking the limit of all of that. So I have the limit as t approaches negative infinity of negative t e to the t minus, now I'm going to do this evaluation right here, e to the 0 power, that is 1. And then I have e to the t power, which would be subtracted, so minus negative e to the t, which would be plus e to the t. And I am taking the limit of all of that. Now, this is an excellent review of indefinite, or not indefinite, sorry. Yes, of indeterminate forms. So when we do this here, we now have 3 terms. The limit of this one minus the limit evaluated at this one plus the limit evaluated at this one. I'm going to actually physically split that into 3. So I have the limit as t approaches negative infinity, negative t e to the t, minus the limit as t approaches negative infinity of 1, plus the limit as t approaches negative infinity of e to the t. This one right here is going to cause some problems. When we do this, we are going to end up with an indeterminate form. When we have an indeterminate form, specifically when we have some kind of infinity times 0 indeterminate form, our best option to evaluate this limit is to turn it into something that will allow us to use L'Hopital's rule, which would be 0 over 0 or infinity over infinity. I can do that if I rewrite this with a negative exponent. So instead of e to the t, I'm going to rewrite this as negative t over e to the negative t. Now when I evaluate this, when I think about this numerator as t approaches negative infinity and this denominator as t approaches negative infinity, I do end up with that infinity over infinity different positive and negative signs, but that infinity over infinity form. So in that case, we're almost done with this one, I promise. In that case, I can use L'Hopital's rule and say that this is equal to the limit as t approaches negative infinity of -1 over negative e to the negative t, derivative of the top, derivative of the bottom, L'Hopital's rule, minus, and then I'm going to go ahead and just evaluate these other ones. The limit of a constant is the constant. And then this third term, as t approaches negative infinity, e to the negative infinity power is 0. So now I just have one more to evaluate here, and I really should be carrying down equal signs to make sure we know what we're talking about right now. This is equal to -1 over negative, so just 1. This is going to be equal to e to the t. This first expression, e to the t power. E to the t power, when I evaluate this as t is approaching negative infinity, e to the negative infinity power, that is 0. So I end up with 0 minus 1 plus 0. This entire thing evaluates to -1. So this is a really great problem to go back and review in a couple of weeks when we're getting closer to the test to practice improper integrals from this, to practice integration by parts, and to practice evaluating limits of indeterminate form using L'Hopital's rule. Really, really, really good problem to review, lots of skills at one time. All right, second one. What is happening right here? Second one, we are doing an improper integral situation here. Even though it's not obvious just by looking at the bounds, the 0 and the 3, neither one's infinity, neither one is negative infinity, but we have discontinuity of our function in between 0 and 3. Specifically, we have a point of discontinuity at x equals 1. There's a vertical asymptote of this function at x equals 1, which means that we could be in situations where our limit as x approaches 1 is equal to negative infinity or positive infinity, or does not even exist. What we want to do here is start by breaking this integral into 2, 3, 4, 5, however many pieces we need to break it into, to break it up at every point of discontinuity. In this case, it's just x equals 1. And we would have the integral from 0 to 1 of 1 over x minus 1 dx, plus the integral from 1 to 3 of 1 over x dx. Now we get to a point where this 1 is working almost in a way that the negative infinity worked in the problem before. At 1, this function has a vertical asymptote. At 1, this function has a vertical asymptote, something like this. So we are looking at this issue right here. So we need to work in a limit here as well to talk about the limit as x approaches 1. Because of that vertical asymptote, we need to talk about a limit as x approaches 1. So that would mean that I'm going to change this first expression to the limit. I'm going to use t again. Again, use whatever variable you really want to here. The limit as t approaches 1 from the left of 0 to t of 1 over x minus 1 dx, plus the limit as t approaches 1 to the right, or from the right. I don't know what I just said there. The limit as t approaches 1 from the right, not 1, no, of t, sorry, t to 3 of 1 over x minus 1 dx. And then what we would do here is go through evaluating this, adding them together. In this particular case, I do want to take us through a little bit of this. In this particular case, when we start doing this, we're going to get a limit that does not exist. We're going to get an integral that diverges. So let's do that with the first one. So let's just zero in on this part. When we are ready to integrate this, we are going to get the limit as t approaches 1 from the left of the natural log of the absolute value of x minus 1. Again, remember the antiderivative of this is natural log. And I need to evaluate that at t and at 0. And then I do have my plus all of that. When I evaluate this at t and at 0, I get the limit as t approaches negative, not negative, positive 1 from the left of the natural log of t minus 1 minus the natural log of the absolute value of negative 1. So the natural log of 1, which is 0. So we just end up with this right here. I am approaching 1 from the left here, which means that our numbers are 0.8, 0.9, 0.95, 0.99, all the way up to as close to 1 as possible. It means it's less than 1. So the absolute value I could actually write by flipping this around if we wanted to. Not necessary. I think it's a little bit easier just to visualize if that's helpful for you. And then oh, I just totally forgot the natural log, sorry. Now think about what's happening as t starts to approach 1. As t gets closer and closer and closer and closer to 1, this expression gets closer and closer and closer and closer to negative infinity. So the limit as t approaches 1 from the left of this natural log of 1 minus t expression is going to equal negative infinity. That means that this, I have about 1,000 colors going on here. Let's see if I can get rid of some of this so that I can redo it. That means that this integral right here is divergent. Because this integral is divergent, even when I add on another integral, my total integral will still be divergent. We'll talk about that diverges versus converges situation a lot more in the next BC session next Friday as well. These should be words that are really familiar from your sequences and series study. So that's improper integrals. Two big things just to keep in mind. You have an improper integral situation when one of your bounds is explicitly infinity or infinity, negative infinity or positive infinity, or when you have some kind of discontinuity, specifically an asymptote, in the middle or in between the bounds that you are given. When you're dealing with improper integrals, you have to introduce limits as you approach that positive or negative infinity or that asymptote. So a couple of quick strategies to just talk through those things that we just did. Whenever you're evaluating integrals, start by just simplifying the integrand, so the expression that you are taking the integral of. Simplify it as much as you can. Factor it, add two fractions together, whatever kind of algebraic simplification you think looks obvious, do it. See if it's helpful. Then look for obvious substitutions. And what I mean by that is that U substitution that we talked about in the last session. If, for instance, you have under a square root sign, you have an x cubed, and then outside of a square root sign, you have the 3x squared. You have that derivative. Look for those obvious U substitution situations. Those are the AB type integration things, integration skills. If those don't help us, if those don't give us anything to really work with, that's when we can turn to these harder things. What we just talked about is if we have a rational function, work in those partial fractions. See if you can split your rational function into 2 using some kind of factoring of the denominator. And then hopefully those individual terms, once we do that, are easier to integrate. Or the other thing that we just talked about, if we have a product of some kind of power function and a polynomial, or a power function or a polynomial, and then some transcendental function. So a function that transcends algebra. It is not a polynomial. That's when integration by parts works really well. Very common integration by parts is when we have a nice linear function and then exponential, or some kind of product between a polynomial or a power function and then a transcendental function. That's when integration by parts works really, really well. Integration by parts, again, is undoing the product rule of differentiation. Two things that we did not talk about, but is worth reviewing before you go into this exam. If you are trying to do some kind of integration with trig functions, substitution using various trig identities is often very helpful. And then if you have radical functions, trig substitution, I'll get to that in a second, but trig substitution or rationalizing, some kind of rationalizing substitution is often helpful. And by trig substitution here, I mean, look back into your inverse trig derivatives. When you look at your inverse trig derivatives, they are complicated rational functions involving radicals in most cases. So if we're trying to undo that, if we're going the opposite way, we already have the derivative, we could be using those inverse trig ideas. And then if all else fails, if something doesn't work, stop and try something else. If you start integrating by parts and it's not getting anywhere, stop and look for some other method. Or integrate by parts several times. Try a substitution and it doesn't work, stop, try something else. There's a lot of trial and error that works for these as well. All right, area between curves. This one's gonna be nice and quick. Area between curves goes off of everything that we talked about in the session before this, so the basics of integration session, if you want to go back and review that one. Area between curves means essentially we're going to find the area between one curve and the x-axis, and then find the area between another curve and the x-axis and subtract them. So I'm going to illustrate this with this particular example. So we are given two functions, y equals sine of x and y equals cosine of x. And then the vertical bounds, x equals 0 and x equals pi over 2. So this is giving us a situation, let's check my art skills today, that looks like this. We have sine of x. I'm gonna actually start drawing cosine of x first. We have cosine of x. We'll say that looks like this. And sine of x, which would look something like this. And this would just keep going on forever, but I know that I am going to bound this with x equals 0 and x equals pi over 2. And I know that cosine of pi over 2 is 0, so x equals pi over 2 is right here. Those left and right bounds are very important for area between curves. We need to know where we are looking from a left and right perspective. When we are trying to find the area between curves, we are going to need a top curve and a bottom curve, and a left bound and a right bound. So we need left, right, up, and down in order to find the area between curves. So now in this particular sketch, this beautiful sketch of sine of x and cosine of x, we have one point of intersection right here. If you know your unit circle well, you know that this is pi over 4. If you don't, you can set these functions equal to each other and solve. I guess if you don't really know your unit circle well, solving sine of x equals cosine of x is not going to be that fun. Or you can turn to technology. Either one, whenever we have a point of intersection between two curves, we do need to know what that point of intersection is. Because in this particular case, and in any case where we have a point of intersection between the curves that is between our x bounds, we will need to use that point of intersection to break up our integrals. So when we are looking to the left of this point of intersection, so from 0, I'm going to draw one more line in here. And we're going to pretend that that connected really beautifully. From 0 to pi over 4, I have my cosine curve on the top. And what I'm going to have to do is find that integral, that area between 0 and pi over 4 under the cosine of x curve. And then I'm going to need to subtract all of this area under the sine of x curve. Then between pi over 4 and pi over 2, we need to flip that around. Now my sine of x curve is on the top. I want to find the area under the sine of x curve. And then I want to subtract the area under the cosine of x curve. And that will leave me with just the area that I want, which is the area between the curves, this and this. So setting that up, we are going to be able to go from, let's see if I move this, if I can write and not take this away from your line of sight. We are going to go from 0 to pi over 4 and integrate cosine of x minus sine of x. I want the area under the cosine curve, or between the cosine curve and x-axis, and then take away the area between the sine of x curve and the x-axis. And then I want pi over 4 to pi over 2. In this case, I want to integrate sine of x minus cosine of x. And from there, that's straightforward integration. That's a calculator problem, or just brute force, go through it, do all of the integration type integration problem. It's the setup that we want to be really concerned about here. One fun thing to recognize here is that the area of these two halves are the same. And we could instead write this as just one of these integration expressions and double it, because this area is exactly the same as this area. So big key, area between curve, top curve, bottom curve, left bound, right bound. You need 4 pieces of information. Anytime you have a point of intersection, that's going to most likely break up your integration expressions. It's most likely going to flip your top and your bottom curve. Now I want to do that exact same thing, except do everything the opposite way. So now do everything in terms of y. So 2 new curves here. We have y equals x minus 1 and y squared equals 2x plus 6. So notice what we're missing first. We are not given a left bound and a right bound, not like the example above where we just have cosine of x and sine of x, and then we are physically told to zero in to this specific area between 0 and pi over 2. In this case, we just want the area between curves. We are going to need to figure out all of the points of intersection and these left and right bounds for ourselves. So when we look at this, let's see what this one looks like. We have a horizontal parabola, and then we have just a nice, pretty linear function. You can turn to a calculator here if you want to. If you were going to graph this in a calculator, we would first have to split this y squared function into y equals the positive square root of 2x plus 6 and y equals the negative square root of 2x plus 6. Hopefully that gives you enough visualization of what this actually looks like. And if we start graphing this, we are going to have the square root of 2x plus 6. So something that looks like this, and the negative square root of the negative square root of 2x plus 6. That y squared function, that's a horizontal parabola. And then we also have our linear function, x equals, not x, y equals x minus 1. So let's say that looks like this. Now from here, this is what we're trying to do. We want the area of this, the area of the region bounded by our 2 curves. This does not have an explicit upper curve, lower curve, left bound, right bound when we're thinking about all of this in terms of x. Before I do anything though, I do want to get these points of intersection so that we have some numbers to work with. You can do this on a calculator. You can do this using systems of equations. Up to you. That's some nice, beautiful, fun algebra. When we do that, we end up with this point right here being -1, -2, and this point up here as 5, 4. Now again, we don't have this clear upper bound, lower bound, or upper curve, lower curve, left bound, right bound situation when we look at the function as it is. But if we turn this function the opposite way, then we do have a very clear upper curve, lower curve, left bound, right bound. When we do that when we flip this function or kind of rotate this function, we have our upper curve as our linear function and our lower curve as this y squared function. And then I have a clear left bound and a clear right bound. So if I flip everything here into terms of y, I can integrate this using the upper curve minus the lower curve. And when I do that, I'm going to come back to my limits of integration. When I do that, my upper curve is the linear function. So instead of writing that upper curve as x minus 1, I need to spin that around so that it's in terms of y and say that x is equal to y plus 1. And then my lower curve is this y squared equals 2x plus 6 situation. When I rewrite that, that is 1/2 y squared minus 3. If I subtract 6 and then divide by 2, x would equal 1/2 y squared minus 3. So there's upper curve minus lower curve. And I need to now integrate all of that with respect to y. Now, big thing to think about, I just switched all of this into terms of y so that I have that clear top, bottom, upper curve, lower curve idea. When I switch all of this into y, I also need to switch my limits of integration into y. So I don't want the x coordinates of my points of intersection. I want the y coordinates. And notice that when I spun this, I kind of rotated my shape, my y-axis now goes backwards. My negatives are over here, my positives are over here. So just be aware of that. If you can physically turn your paper or kind of envision this in your brain, when you do that, most likely your y-axis is now going backwards. So just be aware of that. I want this -2 as my lower bound and this +4 as my upper bound. You could, of course, also go from 4 to -2 and just negate the whole thing when you're done. Up to you. From there, it's just straight integration. This can become a calculator problem. It can become brute force, do all of the integration. When you do that, I'm going to let y'all do that. When you do that, you'll get 18. So big keys there, just big things to think through. When you're looking at your sketch or your graph or whatever you want to call it, and you have that clear upper curve, lower curve, left bound, right bound, as the functions are written, you can do everything in terms of x. If you can rotate your drawing, if you have to rotate your drawing, your graph, turn your calculator screen to the side, whatever it might be, to look at your y-axis as a horizontal axis in order to see that upper curve, lower curve, left bound, right bound, then everything needs to be flipped around into terms of y, and you can follow the same integration. All right, average value of a function. This is super fast. I just want to throw it into this lesson here, this session, because it is a very, very, very forgotten formula. It's a super easy type of formula to use. It's a really quick question add-on. This is maybe part D of a free response question that you already worked really hard on, and then there's just one extra question at the end that's supposed to be super quick, that type of thing. Students just generally forget this formula. So if we want the average value of a function, I'm going to say average value between 2 points. So let's say average value between A and B. The average value of a function, which is generally noted like this, average value of a function between A and B is equal to 1 over B minus A times the integral from A to B of f of x with respect to x. So there's nothing super complicated there. This is math that is much easier than almost everything that I just did for the last several minutes. It's just a very forgotten formula. So just make sure that gets into your formula bank, your formula sheets, wherever it is that you are gathering all of this information. Okay, last thing to talk about, and I want to talk about this one fairly conceptually. Once we figure out how to use these formulas, we just do the integration as we have been doing, but I want to talk about the theoretical setup here. So volume of a solid of revolution. So now we're going to take that area type problem and just add one more step. Start actually rotating that two-dimensional figure around some axis of revolution to create a three-dimensional figure. And there's three general kind of thoughts of volume of a solid of revolution using these three formulas that you see here. So the first kind of big idea here is that the volume of a solid revolution can be thought of using cross sections. So a cross section is some kind of shape section that is perpendicular to the x-axis if we're thinking about this in terms of x. So this sphere, for instance, has a cross section of a circle. If we just keep slicing this sphere into as close to two-dimensional shapes as we possibly can, all of those two-dimensional shapes are going to be circles. This sphere is just made up of an infinite number of circles put together. This is your cross section. And we just have circles and circles and circles and circles forever. We can have cross sections that are really any type of shapes, square cross sections, triangular cross sections, whatever kind of cross sections we want, really. But that's the idea. We take our shape and we start slicing. And what shape are those slices? If we have a shape slice that is nice and easy to find the area of, for instance, a circle, if we integrate that area function between two bounds, so between A and B, then we would end up with the volume of our solid. If I integrate the area of all of these circles, if I threw this on an actual coordinate plane, between 2 points, between some number A and some number B, I will end up with the volume of this entire sphere. That's nice and easy to remember conceptually. The hard part becomes, great, how do I figure out what the area of that cross section is? And again, hopefully this is something that is easy to figure out: a circle, a square, a rectangle, a triangle. If not, then the area of that cross section should be given to you. This is much more of a conceptual type formula. We very often use the next formula as our actual methodology, but it is helpful to think about the idea of volume of a solid of revolution as that integration of an area function if we can figure out the area of those cross sections. But what we generally use in calculus is this disk and washer method. This disk and washer method, where we have something that, for instance, I'm going to go ahead and sketch down here, that for instance looks like this. So let's say we have some shape, let's say it looks like this. Here's my two-dimensional shape. If this was an area question, I would just be trying to figure out the area between this curve and this curve, bounded by this x value and this x value. To turn it into a volume question, I take that two-dimensional shape and I start rotating it around either the x-axis or the y-axis or some other line in order to create a solid. In order to, I'm going to do this one on the x-axis. In order to create some solid that has now a volume, a three-dimensional solid. And now if you're thinking through this idea that this volume of this solid here is the integration or the integral of the area of all of its cross sections, the cross sections of this shape here, I know that it's still two-dimensional, but pretend that this is a nice, pretty three-dimensional shape. The area of this cross section is still a circle. It just has the middle cut out. So it essentially kind of looks like a donut. And if we would try to figure out what that actually is geometrically, go all the way back to geometry, we could find the area of the outer circle and subtract the area of the inner circle. The area of the outer circle would be pi r squared with this radius, and the area of the inner circle would be pi r squared with this radius. The outer radius has a height equal to whatever this function value is. the radius, that inner radius, the radius of the inner circle, has a height equal to whatever this function value is. I'll just call that one g of x. So if we are trying to find the area of this cross section using all of these circles, we would end up with this donut idea, which in calculus we call a washer. So as a natural progression from this down to a more specific formula for this setting, we can find the volume by doing pi r squared minus pi r squared with those two different radius values. Big circle minus little circle, to create that washer idea. If we don't have an inner radius, we don't have that donut, we just end up with a circle, the disk, then this inner radius is just gone. Just a big thing to keep in mind, the thing that I see most often happening to this formula is that that pi drops out. So be really careful that the pi is there. Pi r squared, that's where this is coming from. Pi r squared minus pi r squared. Second thing to note, let me undo all of the things that I just did. Second thing to note, this is not the same as doing pi r, big R, outer R, minus pi inner R, and then squaring the whole thing. I often see a tendency, let's bring this pi out first of all to make this a little bit easier for you to visualize. I often see a tendency to take this square the whole way to the outside like this. Outer radius minus inner radius and square the whole thing. That is not the same thing. Be really careful about that. We can leave the pi. Be really careful about that. You're individually squaring each radius. And then last thing to just note here, cylindrical shells are not part of an AP curriculum. They are a really cool way to find volume of a solid of revolution, especially if you're rotating around the y-axis or any kind of vertical line. If you have a couple of extra minutes over the next couple of weeks and you want to just extend your thinking a little bit further, look into cylindrical shells. The proof of the formula is pretty cool. It's a good application of geometry into calculus. All right, so theory for just a couple of quick minutes. When we are doing a volume, when we are trying to find the volume of a solid revolution, we need to know a lot of information. We have to know what axis or what line we are rotating our curve around, and we need to know if we're bounding that in any way. So for instance, if I have here y equals the square root of x, that looks like this. If I'm going to try to create a solid revolution here, I need to know a lot of things. We need to know what x values we are looking between. Are we going to go from 0 to 4, for instance, and say that, okay, I'm going to take this two-dimensional shape and rotate this two-dimensional shape around either the x-axis and create this, or around the y-axis and create this, or around some other line. Maybe we're going to take this and we're going to rotate it around, let's see if I can get this out of here, rotate it around the line x equals 9, way over here, in which case we end up with a solid that has a giant hole in the middle and then has this kind of shape going on. It's very hard to draw 3D shapes on here. But whatever we are starting with, whatever function we have, we need to know a lot of other pieces. We need to know bounds. We need to know what we are rotating around, because that influences how we think through that disk and washer formula. So I'm going to take the more complicated one to just think through that very quickly. So if I have these curves, y equals x and y equals x squared, I'm going to bound this between x equals 0 and x equals 1, just for the purposes of what we're going to look at here. So that means I don't need nearly that much information. So I'm going to have y equals x and y equals x squared. And that's going to look like this. Make that a little bit bigger. Now, based on our axis of revolution, our radius, inner radius and outer radius, can take many different forms. So let's say we are going to rotate this around the x-axis. That means that my outer radius, the radius from the axis of revolution to the farthest outside point of this new solid, would be this length right there, which we would denote as this function value. My inner radius would be this height, the radius of the part we are subtracting, the radius of that hollow inside, which would be this y value right here. If I were going to change that a little bit and say, instead of just rotating around the x-axis, let's rotate around the line y equals 2. Then we have to think a little bit more. Now our shape is going to rotate around this line. So the other part is not even going to be until down here. We have a much larger gap in the middle. In this case, the outer radius is the function value plus 2 more. And the inner radius is this function value plus 2 more. We want to think through this every single time we're actually working on this. That's if we're rotating around a horizontal line. The x-axis, some other y equals 2, y equals 7, y equals, sorry, this would be y equals -2. Y equals -2, y equals -4, whatever it is. If I change that thought process and say, actually, let's rotate around a vertical line. Let's rotate around the line x equals 0. Rotate this way. When we're rotating around a vertical line, we want to flip all of our functions into terms of y. So we would want x equals something, x equals something else, because now we are going to rotate where we have an outer radius that is this height. That's whatever value of x we are actually at. If we rewrite our functions in terms of x, we would have those values. And then our inner radius would be this value of x. If I manipulate that even more, I'm going to take this one the opposite way that I took the last one and say, let's rotate this around a vertical line, like, let's say, for instance, x equals 7. Well, now my outer radius, so now we're going this way. My outer radius here looks like this. My radius from that axis of revolution all the way to the furthest outside point of my solid. When I relate that to function values, that would be 7 minus the value of this function, or the expression for this function in terms of x. I don't know why I wrote that x sideways. Let me not do that. Sorry. And then my inner radius would be from the axis of revolution to this inside edge of the solid. And that would be 7 minus this function in terms of x. In this case, x equals the square root of y. Or sorry, in terms of y. Solved for x in terms of y. So just think through every single time what type of actual radius you are looking for, whether you need to add a constant value, subtract from a constant value, anything like that. If you can reason through your outer radius and your inner radius, you should be able to set up a disk and washer formula. So let's look at one quick AP problem for this. So one problem, let R be the region in the first quadrant. So we're already given some bounds, enclosed by the graphs of the functions above. So we have f of x equals 8x cubed and g of x equals sine of pi x. Find the area of R, and then write an expression for the volume of the solid generated when R is rotated about the horizontal line, y equals 1. So remember that you can look at these graphs, these pictures, on your calculator. You can try to sketch them, do a lot of algebra. If you're under time pressure, throw them into a calculator. Generally, it's much faster if you're great at typing and practice that ahead of time. So when we do this, our functions look like this. So I pulled this straight off of my calculator so that you can see how nice and helpful that is. We have our f of x equals 8x cubed as this blue function here, and your g of x is this red function. And then we want the area between these curves, the area in the first quadrant enclosed by these curves. Well, that gives me a left bound of 0, but I need to know what this right bound is, this right point of intersection. I don't have any area between these curves in the first quadrant except for this section right here. If you do this on a calculator, I urge you not to just play with the little trace key over and over and over, and actually go into second trace intersect to get the exact value for that point of intersection. So second trace, and you get this menu that you see here, and then intersect. If you have not ever messed with that, not played around with it, do that before you actually take your exam. This will prompt you to enter the left function and the right function, or function 1, function 2, whatever words it actually uses, and then a guess. So we would just hover over the red function, hover over the blue function, and then get as close as possible to this actual point. Your calculator will tell you what it is. So this is the point 1/2, 1. So when we're setting up that area, our area of R is equal to the integral from 0 to 1/2, left bound, right bound, of the upper function, sine of pi x, minus the lower function, 8x cubed dx. And then when we throw that in a calculator, 0.193. One quick thing that I would recommend here, always, always, always write this out, even if you're going to do the actual integration in a calculator. Write down everything until you get to that final point where you're just typing what you see on your paper. Always let the AP readers know what you're actually plugging into that calculator. And then the last one, here's where we get to think about this volume situation. Write an expression. Let me take all of this away first. Write an expression for the volume of the solid generated when R is rotated about the horizontal line, y equals 1. So we are going to rotate around this line. When we rotate around this line, we are rotating around a horizontal line. I just completely forgot what I was saying right there. We rotate around a horizontal line. That means we're going to do all of this in terms of x. We need to know the outer radius. So when we rotate around, we're going to end up with a shape that looks like this, going over and over and over, and just keep rotating that way. That means our outer radius is from that axis of revolution to the furthest outside point on this solid. And our inner radius is from the axis of revolution to the inside point of this solid. So in this particular case, we are going to have to start at 1 and subtract function values. So my volume of my solid here is going to be the integral. So volume equals the integral from 0 to, what was that x value? 1/2 of pi outer radius, which is 1 minus my blue function, my 8x cubed squared, minus pi times my inner radius, 1 minus sine of pi x squared. And I'm integrating all of that with respect to x. Again, just keep in mind that outer radius versus inner radius. Conceptually think through what that looks like in the actual diagram of what you are doing, and then you can generate that formula. These questions very commonly do just say write an expression, because again, once we're here, that's a calculator problem. That's not exciting. They want to see the actual setup. So work through that, conceptualizing that outer radius and inner radius as much as you can. So then those are all of your pieces here for AP Calculus Unit 8, the material that this year is all entirely BC material. Those quick integration kind of skills, integration by parts, linear partial fractions, and improper integrals, and then the keys with area and volume, the conceptualizing of area between two curves and then volume of a solid of revolution. All right, so let me come back to you. So if you have any questions that I have not answered, I think I got through all of them as I was going today. If you have any questions that I have not yet answered, go ahead and throw those in now, if you still have them. And if not, I will see all of you next week. Have a great week.